The dread of the vacuum chamber. The vacuum chamber is required in constructing pyramids because of the simple fact that it is the only way to actually scale the gas wavelength equivalent. So the vacuum inside of a pyramid chamber is not a full vacuum. It's not, I think, what is known as a hard vacuum. It's a partial vacuum. But between our atmosphere and a hard vacuum, or for example, the vacuum of space, where there is barely any atoms within that space. I think it's been calculated to have approximately 1 hydrogen atom per square meter. So it's pretty much a full vacuum. But in between our atmospheric pressure and a full vacuum, relatively speaking, there is a range in which you can scale the gas to correlate to a wavelength. And this is quite simply by using the calculations which derive the value for the Planck mass and placing that within a cube, which the wavelength of each edge of the cube represents the wavelength in the machine. The density that's derived from that directly equates to the pressure that should be inside of the pyramid. And that is the calculation of how you get the values for the pressure inside the pyramid. That will all be covered in more detail in the coming videos. But that is quite simply why vacuum chambers are used, because they assign the density of the gas inside the pyramid, which directly correlates to its wavelength. And there is no exception. There is absolutely none, because it is quite simply a matter of tuning, adjusting the pressure inside of the pyramid, adjusts its correlating wavelength value, and literally is an analog for length. So the pressure inside the machine is directly related to wavelength or length. So you can't have a wavelength inside a pyramid that doesn't have a corresponding pressure, or the pressure that is related directly to that wavelength. So that is why the vacuum chamber inside the machine is required. It is a component that is best not there, but it is absolutely required because it is fundamentally a part of how the pyramids work. So the reason that the vacuum chambers are a curse is because when designing the pyramids, each system, each layer of the pyramid, 1 being the vacuum chamber, 2 being the crystal case, and 3 being the copper frame in most cases, each require a specific set of dimensions. The vacuum chamber inside a pyramid is set up so that it is actually a working part as well, which has a harmonic. So it is not just something that is laid over the copper frame and the crystal. It's very much a part of the harmonic set. And so therefore it is classed as a component. And the reasons for this are to do with the fact of what it is actually made from. In another video, I'll explain how electron configuration works and how each inert gas used for the carrier wave must have a corresponding relationship with the elements inside the pyramid. And the relationship is the electron configuration. For a basic example, argon uses silicon electron configuration. Neon uses a carbon electron configuration. So basically carbon for neon and silicon for argon. And so specifically talking about the vacuum chamber, there are only a few materials to choose from. Basically, neon machines are not designed, or I do not dwell on constructing them, quite simply because the materials available for a neon pyramid are plastic of sorts, because plastic has carbon in it, or even a type of graphene, which is not yet currently available on a practical sense to actually construct a pyramid chamber out of graphene. So the third option is diamond, which is inaccessible. So carbon-based pyramids are a little bit more tricky. So I don't use neon as a carrier wave. Plastic has side effects. Plastic distorts and bends, which is very problematic for creating pyramids. You don't want distortion. Distortion is a problem. Plastic also outgasses, which can be overcome various techniques, but nonetheless, it's still a problem. Plastic also inhibits the etheric field. It restricts the speed in which it would prefer to flow, hence starving the pyramid of energy. A plastic pyramid case should only be built as a last case scenario in order to prove a result which may not even work because of the nature of the plastic. So plastic is somewhere you really don't want to go. The other alternative is to use an argon-based pyramid, which are the systems that I've mostly focused on. The materials that you can use for argon are aluminium oxide, which is otherwise known as synthetic sapphire, fused quartz or fused silica, which is essentially melted down quartz crystals, or glass, which glass is approximately 75% silica. The other problem with glass is that it has many other electron configurations within it, otherwise known as impurities, such as magnesium and calcium, and sodium. So sodium is not meant to be in the glass or the other elements. The idea is to just have one element related to the electron configuration of the gas. So for example, argon for silicon, neon for carbon, and then an element that has an electron configuration that is higher on the periodic table, a higher octave, or an element that is less dense. In these cases, for silicon dioxide, it's oxygen. And aluminium oxide, it is oxygen. And for plastic, it is hydrogen and oxygen. So these elements lighter allow the energy to pass through because they are more transparent, more or less. The energy density is directly related to the elements that the case is made of. So the silicon is going to attract the argon, hyperdimensional energy, and the carbon is going to attract the neon hyperdimensional energy. But to make this most efficient, the oxygen allows it to pass through the case because that is one octave higher and recognized as transparency to this hyperdimensional energy. So it works very well that way. That's how you make a case that is transparent but strong at the same time. And there are other materials that you can make the cases from. There are many, many other materials. However, due to their rarity and the fact that they are not manufactured cheaply or by companies which regularly manufacture them, the cost of creating something would be astronomical. Even a synthetic sapphire case is very, very expensive. The ultimate case to make in regards to creating argon-based pyramids is fused quartz. That is the ultimate. It is strong enough and transparent for most systems. If required, synthetic sapphire can be made. Synthetic sapphire is a commercially available product which is becoming cheaper and cheaper. The benefits of synthetic sapphire are, namely, its strength. So for applications that require higher safety factors, synthetic sapphire is the winner for its very, very strong element. Another problem that the vacuum chamber poses is the fact that its thickness, the thickness of the material, is set, and you are not able to adjust that. The internal dimensions and the external dimensions of the vacuum chamber are based off of a reflection of the harmonics inside the pyramid. This cannot be adjusted, for this would be like trying to adjust the speed of light. So this instantly assigns the vacuum chamber to a specific thickness. And unfortunately, most of the vacuum chamber thicknesses have quite a low safety factor because of this. I spent a long time trying to figure out how to make cheaper vacuum chambers and a lot of stress with that. The current price of constructing a fused silica vacuum chamber or a fused quartz vacuum chamber is many thousands of dollars, approximately between $50,000 and $75,000. Synthetic sapphire is much, much more. The alternative of this is to create a vacuum chamber made of glass. However, this is not preferable because I cannot predict what will happen because of the many other impurities inside the glass, being sodium, magnesium, and calcium. These are other electron configurations which are on the same line as argon and lower, which is quite problematic potentially. The only real way to do it is to have the correct vacuum chamber. However, it is possible that a result may be bad from using glass. Glass vacuum chambers were not possible to create for me up until more recently because the glass simply wasn't strong enough. Glass ruptures at approximately 2,500 psi. That's the mode of rupture for glass. Quartz is approximately 7,000 psi. However, using a very special method which I have experimented with and successfully achieved, I've managed to strengthen glass all the way up to 15,000 psi, which is more than double quartz. And the test has confirmed this, which I will explain when we go outside. But essentially, I've strengthened a panel to the point in which it surpasses quartz, or at least double quartz, to have a safety factor of 1. The way this is done is a method that is not so much used in Australia, but is used in the States. It's quite simply submerging the glass in molten potassium nitrate. The method I use is submerging the glass in potassium nitrate at 430 degrees for 8 hours. That seems to be the optimum for results, where I have conducted many, many tests on vacuum and tried various different panels in order to achieve an outcome which was most desirable. I'll show you all the test panels that I made. There are quite a few. There are many, many results, and I spent months trying to figure this out. The potassium nitrate was the winner in the end. So I'll show you the panel that's in the rig outside, and I will illustrate its dimensions and show you using a calculator what its safety factor actually is. So you'll be able to see how strong it has actually become based on the calculations, which we'll use an online calculator to understand. So its safety factor of 1 is equivalent to approximately 15,000 psi, which means I can finally attempt to construct a vacuum chamber using glass without freaking out that it's going to blow up in my face, because it's quite a problem. Even the concept of a large volume of evacuated space that could potentially implode. It could be lethal, unfortunately. But this is why safety measures are employed in order to try and avoid being in proximity to a vacuum chamber when it blows up. So I will illustrate some things and show you the test panels in the next part of the video. The footage you're about to see illustrates what happens when panels explode. So I knew these panels were going to explode, but I was just basically seeing what pressure they exploded at. And so in the video, you'll be able to see the pressure gauge as well. So you can see the pressure gauge going up, and they both explode at approximately the same pressure. So I've done this many, many times, and this particular time I recorded it so that you can actually see what happens and what it looks like. And out here in this rather messy setup, because I've used it so many times, is my test rig for testing vacuum panels. This one is for the sides of a pyramid. So this is 2mm PMMA plastic supported within a frame, which it will, as you can see, flex if I push it. This one is the panel that actually survived. And it may look a little bit bizarre because of the fact that there is so much glass in the bottom, and that is just to do with laziness. I didn't clean out the glass from the last experiment because I had done so many experiments before. So this rig is on its side. Normally it is on its face so that the glass within that wouldn't affect it. But this glass panel actually survived. And not only did it survive, but it survived on high vacuum for 5 days, which is long enough for me to give it a safety factor of 1. So this has been treated using the potassium nitrate. I treated it in a glass kiln, which I will show, at cone 84, 430 degrees Celsius for 8 hours. And the way I did it was quite simply by putting the glass inside of a bowl containing potassium nitrate salts. Once the potassium nitrate salts melted and acted upon the glass, when it solidified and cooled down, I took the bowl out and quite simply rinsed the potassium nitrate salts until they dissolved off of the glass and left just the glass panel remaining. So this is very, very impressive to me, because this panel, although it flexes a lot when under vacuum, which you can physically see at the surface, it's bowing inwards, it lasted 5 days. Under full vacuum, it's only 2mm thick and 126 millimeters in diameter. That's the free space. And so this is a practical way to test the safety factor of a vacuum panel because it's actually practical, because the results speak for themselves. These panels made the same way consistently survive the vacuum. The ones that aren't strengthened implode at 80% vacuum. So they don't even make it to the full vacuum. But once you make it to the full vacuum, you need to be able to have the panel in that environment consistently. So the panel needs to withstand that vacuum consistently. It can't just be the full vacuum and then release, because it will continue to weaken and the microcracks will continue to grow under full vacuum. But 5 days is long enough to satisfy me for my experiments. So let's just say that after 5 days, this has a safety factor of 1. Now, the prototype in which I need to build, if this ends up being a safety factor of 1, the prototype that I wish to build will have a safety factor of 3. So the panel in the prototype, if I am to make it from glass, is thicker than this one and will calculate to having a safety factor of 3. So technically it's going to be 3 times stronger than this panel. So this panel survived, but it will be 3 times stronger in theory, which is a good start. A safety factor of 3 is good enough for me. It's the best I could possibly achieve of all the testing I've ever done in various methods and various ways, which I will show you all the test panels. But essentially, this is the winner. And if glass will actually work for the prototype and all of the impurities in the glass are not going to affect or disturb it too much, then this will allow for the result. If not, it would be preferable as well to just go for the silica case. But to do with the extreme cost on that, the glass may be first. To have waterjet cut the glass panels with the mitered edges and everything to make a glass vacuum chamber, that might only cost a few $1,000s, opposed to having a company machine the fused quartz from a block and make a vacuum chamber out of that material. That would cost between $50,000 and $75,000, which is much, much more. And much, much more stressful because of the cost in procuring this part. But that is my current progress on having a relatively cheap vacuum chamber that will survive the pressure required for the thickness of the panels for the vacuum chamber required for the prototype that I'm working on. And here we have a good online calculator resource. So this calculator is probably the best one that I use, quite simply because it has more variables that you can actually customize. So hopefully you can see the screen here, but basically if you put in the free diameter that is under vacuum, which is 126 millimeters for all of my square test panels that fit into that rig, and you choose a material which has a preset mode of rupture. So say if we choose BK7, which is approximately the same as soda glass or window glass, which is a mode of rupture of 2,400 psi. So that's what it is. The vacuum pressure is at full, being 14.7. Full differential, meaning practically a full vacuum. And adjusting the safety factor allows you to see how thick it is supposed to be. So for 126 millimeters free diameter, for just standard float glass, the safety factor being 1, meaning the minimum before it implodes, would state that the glass needs to be at least 5 millimeters thick. 5 millimeters thick for a safety factor of 1. So that's pretty thick considering that I've got it down, all the way down to 2 millimeters. So basically speaking, that's why those glass panels blew in the footage at 80% vacuum, is because the safety factor is way below, because those panels in the footage are 126 millimeters of free diameter and they are 2 millimeters thick. So they're well below this 5 millimeter for the minimum safety factor. So I know, because of the actual results in the experiment, that, for example, if we assign the thickness to, or the material to fused silica, a safety factor of 1, the panel thickness must be 3 millimeters in these calculations. 126 millimeters free diameter. The thickness must be 3 millimeters for a safety factor of 1. However, using a custom modes of rupture, if I type in 15,000, which is more than double the quartz, and have a safety factor of 1, the equation answer is 2 millimeters, which is what's in the test rig. So I know that for a safety factor of 1, I can use a safety factor of 1 for 15,000 psi lasting for 5 days. So I've tested multiple panels and they've both lasted 5 days. So I can assign that and use these values because the results in the actual testing speak for themselves. The results are, I guess, the most accurate way to test something because of the different variables in which I'm testing. I'm using square panels, which affects many different variables. So the final results tell me what exactly is going on and what I can use and how to calculate the safety factor from there. So obviously those panels are shrunken down. The pyramid is not, the pyramid panels are not 2 millimeters thick and they're not 126 millimeters in diameter of free space. They're larger, but I've scaled the whole system down just so I don't have to have test panels so large because it'd be quite expensive to keep testing them and create much, much more glass everywhere. So basically, scaling it down a specific ratio, I know that I can get a safety factor of 3 because scaled down, if I put this in, safety factor of 3 equals 3.58 millimeters in thickness. And that is the scaled down thickness of the pyramid panel thickness that I'll be using. So that's how I derived my calculations, through actual results and using this calculator almost just as a ratio calculation, using the modes of rupture as a baseline so that I can actually understand how much stronger a thicker panel is, because it's not a linear calculation. A panel, for example, twice the thickness of another will have a safety factor of 4. So for example, if a panel 2 millimeters has a safety factor of 1, the way these calculations work is that a panel that is 4 millimeters thick, which is double that of 2, will actually have a safety factor of 4. So it's 4 times stronger. And that obviously has to do with the square root of 2. But I would rather honestly use a calculator like this than the actual equation, because this is the actual way to use the equation in a calculator. But this calculator is available and I can easily punch in the parameters, so that's why I've chosen to use it. And it prevents mistakes from being made as well. So that is the theoretics of calculating a panel safety factor. This website is obviously called Window Thickness Calculator from Montana Instruments. Again, this is the vacuum equipment that I use for evacuating pyramids and doing vacuum tests. You see here an analog gauge. Over here you see a digital gauge for higher vacuums, and a vacuum pump, which I can get to pull a vacuum of approximately 200 microns. Here are another 2 polycarbonate-based vacuum chambers, which are not the same ones illustrated in the previous videos documenting prototype history. These chambers were made specifically to understand how to seal plastic in the vacuum, because plastic responds very differently to glass, and that is because it flexes a lot. And so I discovered a way to seal these plastic chambers using silicon and a strip of plastic attached to that will allow the chamber to flex, being made of this thinner material, but also withstand the full vacuum without leaking, because leaking is what happens a lot. And unless you understand, well, I did the experiments to prevent that. So these will be stable at 1500 microns of mercury. That is where they stabilize, and that is because of the outgassing of the plastic. So they will fall to that pressure range, which is acceptable for the pyramids because there is less pressure than that inside the pyramid, is lower than that, but that is the highest you can get the vacuum. Stable. So this will last at 1500 microns for approximately a day. It will drift 100 microns thereafter per day. And so as you can see, this one has a square reinforcement. So these are polycarbonate based pyramids, and it's reinforced at the base with a square, which is not ideal at all, but the base panel is much weaker than the sides. So that must be done. Otherwise the panel will flex so much it will interfere with the geometry of the pyramid and all of the components on the inside. That's why I steer clear of plastic. Not to mention that it is restrictive to the ether as well, and you can only use it for electron configurations of neon and helium. That is a glass attachment. That is a glass circle to let the exhaust out from one of the discs, because the glass obviously is more transparent than plastic. And here's another one. This is larger. This one is actually the height of 3 times the plank length. So this one, which I'll get into all that maths, this one is like the universal baseline. Plank length runs from the third of the pyramid to the apex in this dimension. So the plank length is scaled up so that this is tuned to the plank length. So the plank length runs from the center of this pyramid, its harmonic center, which is 1/3 from base, to the apex. So that's actually 1 Planck length. Scaled up many octaves, but it is the same. It is within that range. It is one of those octaves. And so this one again is made of polycarbonate. I made these myself the best I could. They're not easy to make, and the angles always seem to drift. Even if it's a millimeter, it displeases me. So for example, this one has ratings on it. Everything has markings. And as you can see, what I've written here for this desired outcome is that this one was being tested. So 11 millimeters flexure. It will flex 11 millimeters at 27.5% vacuum. So that's what I wanted to know. So that's the value that I got. So I wanted to know how much it flexed at that percentage. So that's what it is. That's what it rated at. And so, yes, these are two of many, 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 many chambers that I have made for testing. That's just the inlet hole, or the outlet hole, I should say. Outlet for the vacuum, for the air, and inlet for the inert gas. But these were never intended to be made into machines. These are for testing the properties of plastic. And just part of what's required, if you're really serious about this stuff. And although the original prototype fit inside of one of these, it was never. This was never used for anything other than testing. And I have made this shape and this actually the dimensions of this pyramid at least 12 times out of different plastics and for different prototypes. So it has been around. But this is the last one I think I'll be making because I've concluded with these tests and also concluded with using plastic because I now understand that it is not the way and it is not what the pyramids are meant to be made of for various reasons. I have a suspicion that plastic's not even registered in the hyperdimensions, which means that it is not recognized as an element you use to construct pyramids. So, those are just a log of 2 additional chambers. So this is the electric kiln that I bought off of Gumtree. It's a fine beast. It's quite a large one, as you can see. I paid about $800 for it. It's an older one, but it's been refurbished and fitted with a digital controller, so I can control time and temperature using that. And I bought this specifically to chemically strengthen glass as a method for strengthening the vacuum chamber using a high ion exchange process. There's a video on YouTube of a guy that explains this really well. I think it's called How to Make Gorilla Glass. But the process is called high ion exchange using potassium nitrate, molten potassium nitrate. So that was the reason that I purchased this. And it's large enough to do smaller sized pyramid panels. So this is the potassium nitrate that I bought from a chemical company, Redox, I think it is. And this was a siphon that I attempted to rig up to suck out the molten potassium nitrate, but it didn't work because it froze as soon as it got out of the pipe of the kiln. But essentially, just by placing a tray here and submerging the panels in this salt is all that's required. If the panels are larger than this diameter, they have to be stored vertically in the kiln, which is not as easy to process. So for the flat ones is preferable, and the diameter of this is about 400 millimeters. So that's sufficient for all the prototypes except for the one that I actually want to create. But yes, this is the backup plan essentially. And it's proven its worth because the panel did survive. And the process does, in fact, work very nicely. I'm quite impressed by the results. While I'm here, I thought I'd also take some footage of this large, home-built for a TAFE department, flat lap or lapotry polisher, reciprocatory. Oh, and there's glass on it. Reciprocating lap. So the idea for this was to get the glass panels machined and then grind them down and polish them. Grind them down to a specific thickness and polish them using this to get the correct thickness of the vacuum chamber so it fulfilled the correct dimensions exactly. But this was quite difficult to do, and there were some problems. I ended up managing to do it, but for other reasons, I gave up on that prototype and abandoned its construction, which will be explained in other videos. But I did use this machine. There's still some grit here that needs to be cleaned. And this is just a glass panel that I was obviously testing out. That's been water jet cut to have a specific angle. I had a nightmare time with one of the companies. I'm not going to name who they are, but I was very disappointed because I was very stressed because the glass panels cost a lot of money to get cut, the large ones, and the tolerance was out by 2 mils, which is a lot. And I guess I didn't really like their attitude about that, but we'd already paid the money, and that was that. But yes, this was purchased for about $300, and the motor was installed, and it was leveled and calibrated, and it works quite well. And I will be using it again, but just not until I'm required to construct another prototype. I would prefer not to use glass. For many reasons, I prefer to have it nicely machined and just use fused silica, which is supposed to be used. As you can see, Pyramids and Mess have overrun this room. This room's just storage now, because I don't actually live here at the moment. But it's gone to wreck and ruin slightly. But never fear, it will all be restored to its operational function. So, just a quick extra bit in the video. These are all designs which I will be illustrating at some point in the future. Well, that's actually just one design. Here are a few others. These are what I was going to attempt, but didn't. I pulled out at the end. And as you can see, I had prepared a whole inventory of test subjects. Not test subjects, these were actually vacuum chambers that were going to be made. Here's the design left over from one of them. This is the JPEG printout of what the design for the machining looks like, essentially. Oh, it's a small one. We printed this out to measure the tolerances. Because there was an error. But this is good. This one would have been good. This was made by a good company in Sydney. It's just acrylic plastic, or PMMA acrylic plastic. It's not been put together, but it's much thicker and would have been a fine vacuum chamber if it was constructed, minus the fact that it's plastic. But as you can see, there's a lot going on here. They're all water jet polycarbonate panels plastic here. Water jet glass, 8mm thick panels. So I was going to build different materials to test everything. Plastic one, same dimensions in glass, 8mm thick, 8mm thick. And the 15 and 17mm thick varieties down here. Very thick glass, extremely heavy. And this was on the flat lab. This was what I was having processed with the machine. And you can see the edge work here and what I was doing. It wasn't finished. It wasn't finished. So these are very heavy, and the vacuum chamber would have been that big, very, very large, very intimidating, very dangerous if something went wrong. Very hard to chemically strengthen. It was a big ask, and I got really stressed out doing it. So yes, there's a lot of there is a lot going on here, but it was all put aside because something felt wrong. I just had the very clear message to stop focusing on this prototype. This was the equilateral prototype and a 60-degree system I was trying to make work. That one, essentially. I was trying to get it to work, but something went wrong in the process, and not to mention all the obstacles. And I just had to stop because I got the very clear impression that I should only be focusing on the one that came in the beginning. The one that came, and these are others. I call them the lost children. But there are other ones are lost until they're found. They're all ratios of all of the ones that appeal to me. And here we have some show and tell. So what I'm going to illustrate are all the test panels in which I constructed, the ones that survived. There were many, and the only ones that I am able to show are the ones that obviously survived the testing. And yes, just a point of interest in the many tests I've conducted. Because the vacuum, as I said, is the ultimate obstacle, and it is very stressful and very dangerous, especially when the chambers must be very thin. Unfortunately, that's just the way it is, and that is why so much testing needed to be done. So this one is frosted glass. The first one, I can't really remember its history, but the glass was frosted in order to scratch it, I guess, to conduct one of the tests for some particular parameters. This is a polycarbonate panel, which is reinforced in a way which is actually very effective. And it's simply by using octave geometry, stacking and gluing polycarbonate sheets together. So you have originally quite a thin front sheet. This one's 2mm, and with the addition of a 4.5mm polycarbonate and another 4.5mm or 3mm polycarbonate backing. So all the stress is on the second and third panels mostly. So you can see the glue messed up here a little bit, but it still worked. And yes, that one was a winner to a degree. Here's a little miniature test rig that it's actually made up. A whole little area with its vacuum inlet there. But yes, you can see the front panel here, which flexed, and I would have been finding out how much that flexed based on this diameter. It says 1.1 millimeter on it. This is how much it flexed, so that's obviously what it was. Full vacuum would have flexed approximately 1.1 millimeter for a 2 millimeter thickness. And here's another cute little test rig for smaller panels. Whatever I was up to, I can't quite remember. But again, 2 millimeter flexure for a 2 millimeter panel for this triangle, which you can see flexes when I do that. And this one's reinforced as well with 2 panels. Flexes, as it says, 2.2 millimeters for that. So there are hollow cavities in there that I've made. That's actually hollow. They're hollow so the panel can flex inwards, and you can see the hole there for the vacuum, which I've taken out and reused for something else. So there's that little one. And we have here another one. So this will flex 4.5 millimeters under full vacuum. And this one's actually a thickness of approximately 4.5 millimeters as well. So it's unison. And obviously this is for this is polycarbonate, and a reminder, all these are the same dimensions of the other panels, which have a free diameter of 126 millimeters. So they're all the larger, those square ones are the same. This is a strange thing. This was blown using heat and pressure. I tried to vacuum form polycarbonate to reinforce. It was just a complete disaster. As you can see, I figured out a better way to do it. But yes, that still is a panel, technically speaking. And next we have a triangle, which is interesting. Methylene chloride I used to try and glue polycarbonate here to fuse. Methylene chloride's a solvent for polycarbonate, and I tried to fuse plastic onto the front, but you know what's happened? It's warped the whole thing permanently. It's created internal stress or something, and it's altered its dimensions, and that was a write-off. Literally started kind of melting the plastic. But yes, that was a triangular panel with a reinforcement on its face. Another one, I got no idea what happened there, but this looks like such bad craftsmanship. I must have been a bit stressed out. This panel is really cool because I actually cast this. This is cast from epoxy resin, and what's so cool about it is it's actually a lens, because I don't know if you can see that effect, what it's doing. You can see it on that angle, but it's curved ever slightly. It's curved in the middle. It's actually on a warp. It's warped. Sorry, it's bowed. Because the way I made this was that I poured the epoxy into a mold on a 2 millimeter thick plastic panel, and it was warped inwards at a certain percentage. And so when I cast the epoxy, it was flat on the top, but it had that warpage. It had that curve as well. So it was flat with a curve. I'm not sure what kind of lens that is called, but essentially you can see what it's doing there to my hand as a lens. But because of that, it acts as a lens. And the reason it was curved and cast like that was a way to try and reinforce. I'm not sure if you can quite see that. was a way to try and reinforce the material because of the curvature and how that geometry works. But the whole thing failed. This worked really well. I was really pleased with this. Actually, I like it. It's really cool. But it failed because, quite simply, the nature of epoxy bows under vacuum, and this bowed so much when it was under vacuum, but then it reset. But it completely bowed, so I couldn't use epoxy at all because of its memory. It bowed, and it was useless because of that. It just started sagging. I think sagging is the correct term. You can see the lens nature there and the reflection. You can see the light reflecting like that. Yeah, that's really cool. So I made a lens accidentally. Yeah, but sagged, so I had to abandon epoxy altogether. So there's this one, which is again a single reinforcement plastic, which you don't want to reinforce cases to begin with. These are all desperate attempts. Another little panel to go on reinforcement, the 1.8mm flexure under full vacuum. This one, obviously, I was playing with it too roughly with my hands and cracked it. But this was another attempt to reinforce the vacuum by having a very strong string or wire or something here and pulling away to try and pull out some of that flexure. But that was, again, a very messy, sloppy business that had heaps of problems, and not to mention the ridiculous amount of force required to actually correct that flexure. Another test, this time with a hole in it, to find out if it would crack and how much extra it would flex with a hole in the center, because it does need to be a hole in the plastic ones because of its restrictive properties. The pyramid has a little vent, the pressure, hyperdimensional pressure escapes through, and that hole just ensures, with a glass panel over it, ensures that will escape, because if it can't, the system will deadlock and won't do anything because it's essentially blocked, like a blocked pipe or something. Here's another one. This is glass, and it's got a slight, as you can see, distortion to it, because this was put in the kiln, up to probably 800 degrees, 700 degrees, and slightly melted. So it's a 2mm piece of glass, but it's been slightly melted just to see if that would take the micro scratches out of the surface. So I'm not sure what happened here or the results, but this panel survived. I don't know if I made two and tested one and it blew up, but this one still lives. Or maybe I decided it was no good because of the distortions, and the bubbling in the corner would pose a significant problem when putting the pyramid together. I probably abandoned the idea because of that. And another one, this one's made of glass, not plastic. This is a glass side panel. This one obviously survived. This is glass with epoxy glue, really cheap, nasty epoxy glue, filled with rubbish. But it still worked for these testing. This one survived. It's not chemically strengthened, but it did survive. 2mm with 2mm reinforcement. It lasted at least 96 hours. But again, you can't use this because these are not meant to be on the pyramid base at all. They're majorly obstructive and alter all the geometry, and these are like the last of the last resort. Luckily, I have a solution now, which is better than this, which is the chemical strengthening. Another one, this is a much better epoxy glue, as you can see. It's the ECL30 Loctite or something. It's very, very good product and very hard to come by. People are not buying enough of it, but I think it's awesome for all of these. For gluing glass, it's very, very strong. Clear, it doesn't yellow. So yes, a larger one with a more octagonal reinforcement shape for extra strength, but again, extra obstruction. Another one, this is interesting. This one shows what happens. This one cracked, but I released the vacuum before it imploded, which it would have very shortly after. And you can see the law of how this works, which I learnt, that if you have a panel on the back thicker than this panel, it will always crack, because all the stress is going to be converted to this panel, and that's going to weaken it. So it cracked exactly at the weakest spot, and panels I made similar to this blew up as well. This one survived, but with the evidence or the information by the way it's cracked shows what's going on that panel, and that's how I learned, I guess. So yeah, yep, you can see what's happened. And I learned, yes, you can never have a thicker panel on the back than the front. It has to be the same thickness or thinner. Again, this one has thinner panels, but it survived because of that. It abided by that law. And so this one survived too, 96 hours past. It's the dual reinforcement on the back. As you can see, all 2mm thick. Octave. It's reinforced using the octave. And this is just an acrylic panel. I don't know what it's doing in there, but this would not last at all because it is so thin. It would just warp right in. It'll probably even snap if I do that, because acrylic's prone to snapping and whatnot. And this is a Bizarro panel. It survived, but cracked at the same time, but it didn't completely. It's interesting. It imploded here and here, but it survived where it was reinforced. But it's still, the stress must have been so uneven and all over the place that this square here, it must have stressed it so unevenly and so abruptly, these blew out anyway. But the whole reinforcement survived. It was strong enough to actually survive. But that was such a intense way to reinforce it anyway. And here we have some more triangular panels that have just completely deteriorated. Actually, this is a whole pyramid. Was actually a pyramid, believe it or not, and it's completely warped. The methylene chloride does this to plastic, and so that's why I couldn't use it to fuse plastic, because it just has this awful side effect of just completely defacing the pyramid. But that was actually a pyramid, and now it's just warped plastic that's no longer. And there were little test pyramids. This is one that survived. I know, it's cute. So that's acrylic or PMMA, and that was a test for warpage as well. So that's exactly an octave less than it's 2 octaves less than the that large pyramid chambers in there. The panels lying down flat, it's 2 octaves less than that in diameter. Yeah, and yep, it warped a heck of a lot, but it didn't blow up. And this looks the same, but it's different. This is actually an epoxy cast, which I never tested. But this is really cool. The way I made this was so simple but so effective. It was just the mold laying down flat like that, and rotated, cast and rotated, cast and rotated, cast and rotated, and then cast and set to get one fused hollow vacuum chamber pyramid, which I think is so cool. And even the hole was cast, and the hole for the hole was cast also. And so, yeah, that's an epoxy, just one cast, one fused piece of plastic made from epoxy resin, which is starting to yellow. And I never tested this for the vacuum because I knew it would bow after that other test. So now it's just here, just a little creature beside its friend, which is just, kind of there. And I guess, just signifies what the many different testing processes I tried out. I really thought this was going to be awesome. This one would have been so cool if it worked, but the sagging of the epoxy is just the problem, So this would work, but it would sag inwards. Only after a few hours it would be sagged right in, and that's just no good. So that's pretty much the what was left of the tests, the many tests I conducted in order to cheat the dreaded vacuum chamber. So in conclusion, that's why the vacuum chambers pose a real obstacle. Financially speaking, they're approximately 90% of the cost of building a pyramid. Not to mention the stress to do with the fact that the safety factor has to be high enough to prevent implosion, as well as precautions taken in order not to damage the surface of the panels, because that can severely weaken the glass or the fused silica. It is my dream to one day own a vacuum chamber made from fused silica that is of the correct dimensions to house the ultimate pyramid, or the one that I've been working on since the beginning. That is 90% of the obstacles in order to create a pyramid overcome. The rest is relatively child's play, where it is less expensive and less stressful. I will not be constructing a vacuum chamber of fused silica. There are some good companies in the United States that will do this for me, but for a price. And that is just the way it is. Until next time.